So besides like all of it, what areas give you the most trouble? All of it? I know all of it.
Most of it.
Most of it? Stereochemistry is a hard one because it gets really confusing. And you have to think three-dimensionally. So if you can't visualize 3 dimensions, you can use models, but models can take a lot of time to manipulate. So.
Are we taking requests? Yeah.
We will take requests, yeah. You have specific requests?
It was just the inversion, which ones get inverted. Since you're speaking stereochemistry.
In terms of reactions.
Yeah.
Substitution.
So S2 correct.
Yep. Yeah, we will. I will certainly cover that. I think we'll start talking with Chapter 7 Stereochemistry first, and then we'll talk more about the substitution chemistry. All right. So let's see. What do we got here? I guess I should turn this on. Let's start with stereochemistry. By the way, there are a few reactions, like at the very end of Chapter 6, that we didn't really cover on the first exam. Or the second exam that you might want to look at too. I did put up a list of reactions in a study guide on the exams page, like I did for exam 2. Hopefully I didn't forget anything on it. I did it kind of quickly, so. But that's there. It's on the web. You can download it. It looks very similar like this with the reactions that you should need to know. And some of those summarized informations about substitution and elimination chemistry. Okay, so in terms of stereoisomers, right, we've talked about stereoisomers. We've talked about all kinds of isomers, and in particular, we've been focusing a lot on these issues where we have stereogenic centers. So you remember all of the terms that we've talked about for stereochemistry? Enantiomers are mirror image isomers. That usually takes place when you have a carbon with 4 different groups attached, right? When you have stereogenic carbons or stereogenic centers. Oh, writing is terrible today. There is another way you can have chiromolecules, though, right? Without even having stereogenic centers. And that has to do with molecules which have restricted rotation but are different because they can't rotate around, like aromatic rings that are fixed in a certain orientation, things like that. So the definition, of course, is that its mirror image is not the same molecule. You can't superimpose them. Okay? On the other hand, all other stereoisomers that don't fit into this category of enantiomers are considered diastereomers. That includes both those diastereomers which have differences in stereogenic center configurations or in cis-trans isomers. Okay, that cis-trans isomers aren't necessarily chiromolecules, right? They don't necessarily have asymmetry or mirror image isomers and things like that if you were to look at it. E and Z would be cis-trans diastereomers, yes. E and Z, cis and trans on a ring, all of those. Okay, but let's really go through some of these examples. I think I have a blank page here just to write on. Okay, I guess I should see what the book has. We have carbons which have 4 different groups attached. We need to be able to figure out what the configurations are, right? So when you have A, B, C, and D on a tetrahedral carbon, we have specific rules to name those. And we have the R and S configuration, right? So how do you determine R or S configuration for a specific stereocenter? Clockwise and counterclockwise if the hydrogen is pointed towards the back, right? So in this case, if D is the lowest priority group pointed toward the back, and if my letters are in order of priority here, this would be going from A to B to C counterclockwise. That would be the S configuration. Okay. Well, let's look at some specific examples. Some that might be a little more difficult. Let's see here. I'm taking a look at an old practice exam from an SI instructor. That's not good. Okay. How about something like this? Okay, how would you assign the stereocenter here? So this one carbon at that point is a stereocenter, a stereogenic center, right? There are 4 different groups attached to that. You have to assign priorities. So this carbon is attached to 2 oxygens and 2 carbons. So what's highest priority? What's lowest priority? The oxygen is highest, but we have 2 oxygens. Yeah, the one attached to carbon. So you have oxygen attached to carbon, you have oxygen attached to hydrogen, so this is going to be number 1. This is going to be number 2. 3 is the carbon here, that's right, because it's attached to another carbon, and then this one would be the lowest. Now notice, there are stereogenic centers that have the lowest priority group is not necessarily a hydrogen. If there's no hydrogens on the carbon, then it can't be a hydrogen as the lowest group. So, although we get used to seeing most of them having a hydrogen on it, and we know automatically that's the lowest, not necessarily. Okay. So then the configuration is R, that's right. So the lowest priority group is coming out towards us. So you go 1 to 2 to 3 is going counterclockwise, but you need your right hand to do that, right? Right hand. Okay, let's take a look at something like this. I want you to tell me what the relationship between these molecules are. Okay, 2 molecules. They're stereoisomers of each other, obviously. Or are they? Maybe they're the same. Maybe not. Are they mirror images? Not mirror images? Identical? Diastereomers, that's right. So what have we done here? We have 3 stereocenters in this molecule. The bromide here, this center is 1, 2, 3. It should be the R. Okay. Let's see, H would be 1, 2, 3. This would be the S configuration, and 1, 2, 3 would be the R configuration. So if you look at this, the molecule next to it has some of those being the same. This center switched R to S. This center switched R to S, but this center is the same, S to S. So if you have a hard time just looking at the structure and seeing that, and this is a pretty easy one because the ring is drawn the same way, the groups are in the same place, so it's easy to visually see that. But if you have a molecule which is drawn differently, it might not be that easy to see. One way is just to look at and determine the R and S at each center and then compare it to the other molecule. Okay, an example of that might be something like, let's see, I like to do tricky ones sometimes, so. Okay, let's take a look at something like this. Okay. These are two isomers of the same molecule. But I've drawn them in different ways. And so it may not be apparent necessarily what the relationship is, but you have to compare. This has two stereocenters in the molecule, so you really need to compare each one from one molecule to the next to see what it is. Okay? So who can see this immediately and know what the relationship is? Enantiomers, diastereomers, or identical? Would they be identical? We have one person say identical. Who agrees? You agree? Okay, two people. How do you figure that out? Well, notice, be really careful, because what I've done is I've drawn the carbon backbone differently. So here's our 4-carbon backbone, and here I've drawn it like this. So I've actually rotated that middle bond from one drawing to the next. But the best way that should be foolproof, if you're good at determining the RNS configuration, is to do that. So at the alcohol stereocenter here, we have 1, 2, 3. This would be R, and the other one Cl. 1, 2, 3 would also be R, right? Do the same thing for this molecule. I flipped it over a little. 1, 2, 3 would be R, because the hydrogen's coming up. And then the chlorine, 1, 2, 3 would be R, the hydrogen's coming up. So we haven't changed anything. We have R at the OH, and we have R at the Cl carbon, and the same thing here, R at the OH and R at the Cl. So if you write it out or do something like that, it's sometimes easier to see that. Those are identical. That's right. They are identical. Okay, they wouldn't have to be. So, are you having trouble still seeing RNS configurations? You're not. You're getting this right away. That's good. How about the rest of you? Meso. Oh yeah, meso. We should talk about meso compounds. What is a meso compound? A meso compound. There's a plane of symmetry in the molecule, but if you take a look at, benzene has a plane of symmetry. Actually, lots of them. Okay, is benzene a meso compound? No, it has to have something else. 2 or more stereogenic centers. That's right. 2 or more stereocenters. So a good example might be something like dimethyl, 1,3-dimethyl cyclopentane. Okay, there are a couple of isomers of that, cis and trans isomers. Oops, sorry, I messed that up. So if you take a look at the cis and trans isomers of this, right? Those are diastereomers of each other, cis and trans, but are they chiral? Are they not chiral? Is there a plane of symmetry? Right? The molecule on the left does have a plane of symmetry. If you bisect the molecule right down the middle like that, one side is mirrored to the other side. So if you held a mirror bisecting that molecule, you would see the same thing. This one, however, if you take a mirror right down the middle, it's not symmetric from one side to the other, because here on the top there's a hydrogen, and on the bottom here is the hydrogen. So if you reflect this over to the top side here, it's not the same. Right? So if you do, since there is no plane of symmetry that you can find in this molecule anywhere, if you take its mirror image, it's going to be different. So this is a chiral molecule, and this is an achiral molecule. Achiral because its mirror image is identical, although it has 2 stereocenters on it. Okay, they are carbons with 4 different groups attached. But because of that symmetry, it is meso. Meso compounds are achiral. That's right. In order to be chiral, the mirror image has to be different. It has to have the ability to have an enantiomeric isomer. Meso. Okay, let me just take a look at the chapter. Enantiomers, stereocenters, symmetry, optical activity. Do you know what optical activity means? How it behaves to plane polarized light. Yeah, it is called optically active if it changes the rotation of plane polarized light as that light passes through it. And that's the property of being chiral. So if you have achiral molecules, nothing happens to the light. If you have a 50-50 mixture of enantiomers, a racemic mixture, it also will not rotate plane polarized light because each enantiomer rotates it in the equal amount in the opposite direction. So if you have an equal mixture of the 2 mirror image isomers, it'll cancel each other out. Okay, if you had 90% of one enantiomer and 10% of another enantiomer, you'd see that light being rotated, but not as far as if it was a pure enantiomer. No, I won't have you do that. Good question, though. We do that a lot, actually, in chemistry. Let's see, Kahn-Ingold Prelog. So assigning priorities hopefully is not a problem at this point because we did it with E and Z before, and we've done quite a bit of it now. Be really careful if structures are really complicated. Let's see, there was one on the last exam. Let me see if I can pull that up. Oh, go away. Oops. Somewhere I have the old exam. Okay. So, oh, here's some. Have you guys looked at this yet? Take a look at some of these. Actually, these aren't that bad. But they are a little more complicated than what we had before. So, let's take a look at this one. How would you do this stereocenter? Priorities. We have oxygen, carbon, carbon. We have this oxygen is obviously going to get first priority, right? Here's a carbon attached with a double bond. How do we treat double bonds in assigning priorities? That's right. So you lift that up. So you imagine that the bond is broken and you have a carbon here and a carbon here. Okay, and then this carbon is attached to a nitrogen. So obviously the carbon that's attached to the nitrogen is going to be next, and this one's going to be third. Now we didn't really need to think about that double bond at that point, but sometimes you do. So that's going to be the R isomer. Okay. Those aren't so hard. These are easy ones. I need to do harder ones. Okay. If you want me to do more, let me know.
Are they going to be harder than that on the test?
Good night.
Just go blend out the number.
It goes by atomic number first, right? And so again, just remember, go out as far as you need to in order to make a distinction, but no further. It doesn't matter what's further away. What is there? Properties of enantiomers. This is all easy stuff, you guys. Right. So in terms of reactions that affect stereocenter, so the first thing to note is that stereochemistry is not created. Oh, what's wrong with my computer? It's under control of my iPad. Okay, so chiral molecules can only be generated in a racemic mixture if there's nothing else chiral involved in that reaction. Okay, the only way to control the formation of one enantiomeric or one configuration of a stereocenter over another is to have something else chiral making a difference on either side. So some of the reactions we've talked about which generate chiral centers are things like addition reactions, additions to double bonds, right? So if you take, say R, like an alkene plus HBr, right? You know you generate from this product the addition of hydrogen and bromide across that. So that's a stereocenter. Okay, and I didn't draw stereochemistry because it has to be a 50-50 mixture of the two enantiomers. There's no way to control one way or the other because if you remember, this reaction occurs first by protonation to form a carbocation, which is planar. That planar carbocation then can have the bromide add from either side equally. Okay. There's no difference in the top or the bottom in terms of the energy. There's no difference in the steric environment. The only way you can alter that is to have something else asymmetric, making it somehow different. So if this group, for example, is a chiral group, there's chirality on there, that might actually change depending on how close it is. I think the example we had used before was like a cyclopentene, where we have something like a stereocenter next to it. Now this molecule, if you add, let me make it a little easier. So we have regioselectivity in the addition of HBr. Okay, in this case, if we add HBr, there are two possible products, right? In terms of the Br being on the same side as the CH3 or opposite sides. So CH3 up. Here you would have actually CH3 down and the bromine up. Plus the other product. Bromine down and CH3 up. Which is the major? Now you'll get both, okay, but which is the major product? Which would you expect to be produced in a greater amount? Hmm? The bottom one, right? This should be formed in a major amount. It may not be that much major, but you should expect that that one would have a potential to be formed more readily. Why? Because the intermediate carbocation, even though the carbocation is planar, I'm going to draw this in a side view. Even though our carbocation is planar, and we have this, that's the CH3 on that, we have a difference in the top and the bottom. Okay? This stereocenter right here influences or changes the difference from the top side of the ring to the bottom side of the ring. And that influence is going to be greater the closer it is to the reacting center. If this is further away, there may not be a whole lot of difference. Maybe a little, not a lot. The closer it is, now the more you make the top crowded, the harder it is for the bromide to come in from the top. It's being crowded. It can more easily come from the bottom. So you have two competing paths, and now you've generated more of the reaction where the bromine comes from the bottom. That's how a stereocenter in the molecule can affect the generation of a new stereocenter. If you're lucky, it controls it completely. A CH3, probably not, but let's say you had a tertiary butyl group. Let's say you had a big bulky group. Okay, something like that, which is completely blocking the top of that ring. That you would expect to be more selective, right? You would block it even better. By the way, the relationship of the products. What's the relationship of the two products? We just talked about comparing two molecules, right? What's the relationship between those two? Diastereomers, right. They're not mirror images. One stereocenter stays the same. This stereocenter stays the same, the one that was originally there. The only difference is the configuration of the second stereocenter. They're not mirror images, they're diastereomers. So in the generation of a new stereocenter, the original stereocenter that's in the molecule is influencing that. This is a diastereoselective reaction. So if you started with an enantiopure starting material, if that was only a single enantiomer, then you would have a product which would be optically active, right? So you'd have more of this than this, and this would be optically active, and this would be optically active. If you started with a racemic mixture of the starting material, the products, although you'll have one diastereomer produced in greater preference over the other, you'll still have both mirror images of them. So you'd actually have four products. You'd have the mirror images of both of these. But the diastereomers would be formed in the same amount, as it would even if it's optically pure. Does that make sense? Okay. So this is a stereoselective reaction. Stereochemistry in the molecule is helping to give a preference of one stereoisomeric product over another, in this case a diastereoselective reaction. There are reactions which are stereospecific, meaning some stereochemical element in the starting material can only give one stereochemistry of a product. That's the case, especially when we talk about not necessarily chiral molecules, but cis-trans isomers, like adding dibromide, adding Br2 to an alkene, right? If it's a ring, you'll get the trans addition. That's a stereospecific reaction. You don't see any of the cis. It can't form that way. Okay, properties of chiral molecules, right? The only real property that we have that we're able to easily observe in enantiomers is the rotation of plate polarized light. There are no other physical properties which are different that we can easily control. That is melting points, boiling points, solubilities, densities. Mirror image isomers all have exactly the same for each of them. That's not the case with diastereomers. If they're related as diastereomers, they could have different boiling points, melting points, densities, solubilities, and because of that, we have physical ways in which we could think about separating them. So we can easily separate diastereomers. It's hard to separate enantiomers. So in order to resolve them, if you have racemic mixtures of compounds, like in the first example I showed up here, we can only form a racemic mixture. How do you then separate those enantiomers? Very, very difficult. Sometimes you can have, well, maybe not with a bromide, but with some functional groups, you can add on something else chiral that you have already pure and then separate those as diastereomers. That's a possibility. Okay, meso compounds, multiple chiral centers, reactions that produce stereoisomers, resolution, polymers. Okay, that's all in chapter 7. You have questions about?
So when we're doing like the SN2 reaction,
Yep.
chapter 7.
It's chapter 8, but you can talk about it. So SN2 reaction. So let's talk about substitution. And then we'll bring back in the stereochemical elements of substitution, right? Substitution, where we take some leaving group, which I'll say X, plus a nucleophile, some nucleophile, can be replaced. Just be consistent here, right? Substitution reaction in its general form, but now we know a whole lot more about this reaction process, particularly if our leaving group is a very good leaving group, okay? Very good leaving groups. What are good leaving groups? I'm sorry? Oxoniums, that's right, a good leaving group. So way back in one of the earlier chapters, we were talking about alcohols. They don't come off, but if you can protonate it, those are pretty good leaving groups. Okay? Has to be done under acidic conditions. Water comes off as neutral. OH is hard to come off as an OH minus generally, but water can come off as neutral. Usually those reactions are going by which mechanism? For most of the acid catalyzed reactions, usually they work best when we're looking at SN1 type processes. So carbocations form, right? Now fast forward to chapter 8, where we started to talk about other kinds of nucleophiles that we can do much better control of. Other good nucleophiles, halides, particularly iodides, bromides, and even chlorides, and they get a little bit harder to come off as you get higher up on the periodic table. But those are generally good good leaving groups. Tosylates, right? Abbreviated like that, or I use OTOS sometimes, or PTOS, paratosylate. If you remember that, that would look like this. Paratoluene sulfonate. So any of these sulfonates are really good leaving groups. That line just means it's attached to the carbon you're reacting on. Let's see. That's pretty much what we've talked about, right? Halides and tosylates. Very, very poor leaving groups, as I said. OH, nitrogen, any kind of nitrogen compounds generally are very poor leaving groups. I don't think we really covered nitrogen compounds. They are hard to break, and bonds are not as polarized as they are with those leaving groups. So these are the best leaving groups. Sometimes sort of in between things that come off as a better anion. So if you have an acetate, so that's where it's attached. So this would come off as a an acetate with a CO2 minus. Okay, acetates could be leaving groups. Carboxylates. So recognizing leaving groups, mostly halides and tosylates. What about good nucleophiles? Good nucleophiles. Cyanide's a good nucleophile. Cyanide, azide, N3 minus. Sulfides, and sulfur attached to carbons as well. Okay, notice I'm drawing them as the anion because anions are better nucleophiles than the neutral analogs. And if you have a metal with it, it's an anion. Okay. But for example, thiolate, SH minus, is going to be a better nucleophile than H2S. But H2S is going to be a better nucleophile than H2O. Right? So good nucleophiles. Some nucleophiles which could be good under some circumstances but cause trouble are things like hydroxide, alkoxide. Okay, why are those sometimes bad?
Do they cause elimination?
They cause elimination. They are good bases. They're strong bases. So competing with elimination, if you have hydrogens adjacent on the carbon adjacent to your leaving group carbon, you can always do E2 eliminations quite readily if you have a strong base. And that's usually the case when you have these types of things. Or now that we've learned about another good strong base, NH2 minus, those sodium or potassium amide, those actually are excellent bases, even much better than hydroxide. So these are actually poor choice for nucleophiles, but good choice as a base. So if you want to control this competition between elimination or substitution, your choice of nucleophile and or base is an important characteristic. Okay. So let's talk about the details then of the substitution. So if you take a specific example, let's just take something like this. All right. It's an alcohol, primary alcohol. Not a very good leaving group. But let's say we want to do a substitution reaction. Let's say we want to do one of our, the new substitution reaction we talked about in Chapter 9. We want to convert it into something like this. So what's the nucleophile we need? That's also another good nucleophile, a carbon nucleophile. Right? We just talked about this in Chapter 9. If you take acetylene, in this case, acetylene, and you deprotonate it with sodium amide, you could make, for example, this sodium salt. That is a nucleophile that will react, but that's not going to react with the alcohol, right? If you take that sodium acetylide and expose it to the alcohol, what reaction do you think would happen? Well, no, there's nothing to eliminate. This is bringing in a lot of concepts. That's one of the things, reasons I'm doing this. Okay, so first of all, we make this by taking our acetylene and reacting it with sodium amide, right? That's how we make it, that acetylide. Why do we use sodium amide? Why don't we use sodium hydroxide? Right? This is the proton which is coming off. This is the base. Why not NaOH? You need a base strong enough to take off the proton, right? What's the pKa of acetylene? Roughly 26. That's much more than rough. That's spot on. 26. Okay. What's the pKa of the conjugate acid that if we used hydroxide? 16. 15.7, but close enough. 16. Which is the stronger acid? Water. So the equilibrium would not, you can't deprotonate acetylene with hydroxide, because the conjugate acid is stronger than acetylene. That means the base is weak, is too weak, right? So what does water look like? Water looks like alcohol, right? So what would happen if if you exposed acetylide to that alcohol? It would just do an acid-base reaction, and that would just take the proton off. Right? It wouldn't do any substitution, and I'm digressing a lot, sorry, but all those concepts, right? They're all there. So if our goal is to make this product from that alcohol, what do we have to do to the alcohol? We have to make it into a better leaving group and something that's not acidic, right? What good leaving groups were we just talking about? Halides? You could make this into a halide, right? What could you do to make it a halide? HCl may work, but remember that goes through carbocations. If it were tertiary alcohol, it'd be much better. But then you can't do SN2 on a tertiary halide. What's a better choice? There are two ways we can make halides. The chlorides we can make with SOCl2, or the bromide we could make with PBr3. Either one of those will put either a chlorine or a bromine on there. So I'll just say X. Okay, now we've made it into a good leaving group. Now we can expose it to our acetylide that we generate from sodium amide and acetylene and do the reaction. Okay. There's another way to make the alcohol into a better leaving group. And that is to use the paratoluene sulfonyl chloride. One way you can write it is like this. In the presence of some something to soak up the HCl that's generated, pyridine or triethylamine. That makes those sulfonates now, which are also good leaving groups. That's one of the advantages of, actually alcohols. So you can make those sulfonate leaving groups, and you can then do that substitution chemistry quite readily.
Can you first start with the tosylate and the first?
If I gave you the tosylate, yeah, then it'd go right down, right? If I gave this to you first, yes. But if I didn't give that to you, and I said take alcohol and make this, or if you wanted to put a cyanide nucleophile or some other kind of nucleophile, you'd have to first convert it into a better leaving group. Now, I've just chosen a primary alcohol, but if that alcohol is on a stereocenter, then there are stereochemical consequences, right? Because the stereochemistry is affected by the substitution reaction. So recall that if we have an SN2 substitution, we need primary or secondary substrates, leaving groups. Okay, tertiary is too crowded. It's a one-step reaction, so you have to have the nucleophile come in from the opposite 180 degrees from the departing leaving group. And in that process, this configuration of the carbon inverts. Okay, so if I take, let's see. I'll just use a bromide for an example. Okay. In the transition state, let's say we take sodium cyanide. Now we do a SN2 substitution with cyanide. At the transition state, in this one-step reaction, starting materials, products, at the transition state, Okay, we have bond breaking, so bromine is leaving, and the cyanide is forming. And at the same time, the other three bonds on here are shifting. So I don't know exactly. I don't know if I have the right stereochemistry here or not, but those are the other three groups: hydrogen, isopropyl, and methyl. Did I get the right stereocenter? So in the transition state, as that's happening, the stereochemistry is inverting like an umbrella, and so the product will be the opposite. So if I draw the product, the cyanide will be down. Okay, SN2, complete control or 100% inversion of the stereocenter. So the starting stereochemistry leads to the product stereochemistry, inversion. If it is, if we go by an SN1 mechanism, right? SN1 mechanism, let's say I have something like this, a tertiary bromide which can form carbocations, and I say, let's just take, what's a good nucleophile? Let's just take water, let's just take methanol as the solvent as well as the nucleophile, the only thing present there. No base, no anions. Heat that up. And I should draw stereochemistry here. Heat that up. The product you get is what, if it's the solvent participating as the nucleophile. It's what we refer to as a solvolysis reaction. So this will form a carbocation first. Okay, and what do we know about that carbocation intermediate? The stereochemistry that was originally on our bromide now is lost because we've gone to an sp2 planar carbon. And then, in this case, methanol, and then eventually taking off that proton, could add from either side of that carbocation, and you end up with OCH3 as a racemic mixture, or probably close to a racemic mixture. Okay. So you wouldn't be able to control that. So you'll get a mixture of enantiomers if you do substitution on under SN1 conditions. Okay, SN1. Now, by the way, the reaction diagram forms an intermediate carbocation and then down to the product. Rate determining step being formation of the carbocation. So what's then, so that's the stereochemical consequences. I've shown you two examples of substitution, one by SN2, one by SN1. What other thing is important for these reactions? What else helps to go one way or the other, or facilitates one of these processes over the other? The solvent, right? This happens to be the solvent and nucleophile together, but it's a protic solvent. It has that OH group. I didn't write a solvent in the top case, but it works best with a solvent which is aprotic but polar. Okay? And there's lots of abbreviations for those. DMF, dimethylformamide, dimethyl sulfoxide, hexamethyl phosphoramide, even acetonitrile. Acetonitrile is a very good organic solvent for dissolving those. It's got that CN group, which is polarized. That's a pretty good solvent, and there are no acidic protons in there.
What's the difference between the protic and the
The protic has a proton attached to an oxygen, which could be acidic. It'll have an OH, yes. These do not have any, sometimes NH, by the way. It's ability to hydrogen bond. So you have an NH or an OH, those can hydrogen bond. That stabilizes and surrounds anions, which is good if you want to stabilize the bromide as it comes off. Then you want hydrogen bonding around it to help stabilize it. But if your reaction depends on the nucleophile, you don't want to reduce the reactivity of the nucleophile by that. So you don't want those protons. That's the reason. Okay, one more thing about the substitution chemistry, tying back into if we want to use an alcohol as a starting material. Okay, if you take a look at, let's just say this. Let's say we want to be able to take this and make that from it. Or selectively make its diastereomer and control it. We don't want to do an SN2 reaction because an SN2 reaction would give us a mixture that we have to separate, and that's a pain. We want to be able to control it. So starting from that alcohol, what sequence of steps would you use to get the product on the top and the product or the product on the bottom? You have to make the alcohol into a good leaving group. You have two choices to do that. You can make a halide, or you can make a tosylate. That matters, which one you choose. So you want to, one of these you need to make the tosylate, one of these you need to make the halide. The second step in both is the same. You use a nucleophile. What nucleophile do we need for to get that group on there? Oh, okay, to make the bromide, yeah, PBr3, but to get this group on, what nucleophile do we need? I'm looking forward. Huh? Well, this is the group we've added, right? So we just need the anion of that. You'd be surprised how many people forget to think about their nucleophile, and I see all kinds of things written on tests for that. It's just the anion of that. So I'm going to write here the second step is something like sodium methyl sulfide. Okay. That's a good nucleophile, right? The S minus of that sulfide. That reaction goes by what mechanism? Good nucleophile, good strong nucleophile, and you want to be able to control. You don't want mixtures. You want to be able to control SN2. Yeah, don't mix up SN1 and SN2. SN2 is the one-step reaction where it inverts. Okay. The 2 refers to 2 molecules involved in the transition state. Remember that. That's another thing people commonly mess up. So now we just got to figure out which of these would give us the right stereochemistry in which to do an SN2 inversion. Okay. So in the top case, the configuration of the carbon we start with at the alcohol is the same as the product. And we know the second step has to invert. So that means what do we have to do in the first step for the stereochemistry? Invert. So if we want to end up with the same, we have to do 2 inversions. Okay? 2 inversions. And if we want to get the product on the bottom, this reaction does an inversion, so we don't want any inversion in the first step. So we need to choose the way to convert OH to a leaving group in the top that will invert the stereochemistry, and in the bottom that won't. So which of those two methods, making a halide or making a tosylate, inverts the stereochemistry? The halide, that's right. Because the halide is also an SN2 reaction. So let's just say I make the chloride, SOCl2. That is also an SN2 reaction. So both of those in two inversions make the chloride, or you could use PBr3 to make the bromide, either way. In the bottom case, you need the paratoluene sulfonyl chloride and then pyridine to neutralize the HCl that gets generated. Remember, that's making a sulfonate but not doing anything to the CO bond. It's only affecting the OH bond. It's just replacing, this tosylation is just replacing the H with the sulfur. It's not changing the CO bond at all. That's why nothing happens to the stereochemistry. In the case of actually changing the O to a Br or Cl, it is inverting because you have to kick off the group.
So it's then it would be on the end of that. It would be O, which is
Yeah, so I'll draw that intermediate, the tosylate. After that first step, your intermediate would look like this. I'll just say R. SO2R, that's the sulfonate. So we've only changed the OH bond, not the CO bond. In this case, in the top, we go to inversion with the Cl. Okay. Any questions on these substitution reactions? Elimination. Let me just come back to that summary. Let go of my. I think I'll put it on here. Oops. I do. Come back, come back. I should have it on that summary in the exams link. Aha. Okay. So just to summarize this, right? SN1, SN2. If you're going to do the one-step reaction, nucleophile kicking off the leaving group, it has to be primary, secondary. It can't be crowded. If it's tertiary, it can't work. It's too crowded. But tertiary is easy to form carbocations. So that helps you. First of all, that would be, if it is primary or tertiary, you know right away SN2 versus SN1. If it's secondary, maybe it could be in between, depending on other conditions. Weak nucleophiles, since it's not involved in the rate determining step, works when you form carbocations. Anything that's even weakly nucleophilic will add. To do this, you have to have a good, strong nucleophile. Leaving groups, yeah. Inversion, mixtures, polar aprotic solvent, polar protic solvents are best. So if you put all that together, that can help you figure out which way a reaction might proceed. By the way, if you get a result, let's say you start with one stereoisomer and you're ending up with mixtures, you know it has to be an SN1. If you get complete 100% of an inverted product, you know it has to be SN2. Okay. Now, elimination. Here are the distinctions for elimination. So, again, substrate plays a big role. All of the primary, secondary, or tertiary, the crowdedness doesn't matter if you're just taking a proton off, unless it's really crowded around the proton. But if the leaving group is on a tertiary carbon, That's not where the base needs to get to anyway to get the proton off, right? So you can do E2 elimination. Anytime you have a strong base, alkoxide, hydroxide, amide, those are keys that the major pathway is probably in E2 elimination, where it takes the proton off at the same time the leaving group is leaving and you're forming a double bond. Okay? With a tertiary substrate, unless you're forming carbocations easily, even weaker bases, as long as you have some kind of anion, it's possible to do elimination. But notice when I compared the substitutions before, primary, secondary, tertiary, those X's show you that also. Primary can't form carbocations. Tertiary can only form carbocations unless you can do E2 elimination. So SN1, though, that tends to be the favored processes with neutral conditions or acidic conditions or solvents. Okay. Here's a list of some of the good nucleophiles. I put acetylide on there. Yeah, we talked about those. Oh yeah, the base. So sometimes if you think about doing SN2 substitution with something like methoxide and alkoxide, you can avoid that if you want to force it to do elimination by making your base really bulky. Okay, so the bulkier the base, the harder it is to do SN2 substitution. So it'll be more prone to do elimination. One of the bulky bases, for example, was tertiary butoxide. Right? So if you have something like that, that's a really good base to use if you want to control it to do only eliminations, because it's just too big to do substitution chemistry. So you could even get away with getting pretty good E2 selectivity over SN2 with a primary substrate. So that, let's see, where's that base, come on, slide. Oh, I can't write and scroll at the same time. That base would work well with a primary alcohol or primary leaving group if you have a hydrogen next to it. Okay. What else is important for E2 elimination versus E1? There's a stereochemical requirement or a three-dimensional orientation requirement for E2, right? Do you remember that? Let me write it for you. So remember, in E2 elimination requires that your leaving group, whatever it is, and your hydrogen be in the same plane and 180 degrees apart. Anti-periplanar or anti-coplanar, right? So let me just draw the other groups here. So your base comes along and takes it off like that. So if you want to do elimination with E2, you have to have the right alignment for the hydrogen. That's really important when you have rigid molecules like cyclohexanes, right? And as a matter of fact, any ring compound, the only way you can do E2 elimination is if there's a hydrogen on the opposite side. So remember elimination. Let's say we react this with KOH or potassium T-butoxide, something like that. What's the product? Huh? Double bond where? So under elimination conditions, it usually favors the most stable double bond, which is the more substituted one. Okay? More substituted, less substituted. However, we can only form the double bond here. Why? This is the only product. In that example, that's the only product. The less substituted double bond. Why? What did I just talk about? There's a requirement. The hydrogen has to be opposite the bromide. This hydrogen is not opposite the bromide. It's on the same side as the bromide. So it's extremely difficult to do elimination there. You would have to change this stereochemistry in order for that elimination to occur. So on the other carbon, there's a hydrogen up, but there's also a hydrogen down. This is the hydrogen which can lead to elimination with an E2 mechanism. If it were an E1 mechanism, if you're forming a carbocation, it doesn't really matter because then the bromide becomes a planar carbon in a carbocation. Okay, so all the concepts you've learned in every chapter along the way up to here, they're all mixed together. You can't forget anything. Any more questions on substitutions and eliminations?
So hydrogen has to be add G to it.
Leaving group. So yeah, and that's important because it's the bond. So right, we have the bond here that this is overlapping, and we have the bond which is forming between the carbons and the electrons in the bond here, which are breaking. So it's about how the new orbital is being formed. The new pi bond is being formed, and this one being broken. They have to be aligned properly. Because it's all happening at once, right? In the transition state, the pi bond is beginning to form, and the leaving group is leaving, and the electrons are flowing. So, okay. We should talk a little bit about reactions, right? Reactions you need to know. Reactions of alkenes. There were a few at the end, as I said, which you probably want to just go back and take a look at in the end of, chapter 6. I think like 6.19 to the end. Don't worry about the polymer chemistry. But there were some oxidation reactions that we talked about. One being this reaction. So if I have a double bond and I do react this with what we call MCPBA, you remember what that is? Anybody remember what that is? It stands for metachloroperbenzoic acid. Not that you have to know the structure, but this is the structure. Metachloroperbenzoic acid is an oxidant, and it transfers an oxygen to a double bond. As a matter of fact, it transfers specifically this oxygen to the double bond. But that's a peroxide because we have an O-O bond. Those are good electrophiles. So what kind of product do we form when we expose any alkene to MCPBA? Not an alcohol. It forms two bonds at once.
Epoxide.
Epoxide, yes, very good. Ding, 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 ding. So it forms this three-membered ring. Okay. The double bond could be in a ring like I've shown there, or it could be an acyclic alkene. It'll form an epoxide. Epoxide. So that's one example of an oxidation reaction that we can do on a double bond. Another oxidation reaction. I'll do it on this one actually. If I treat this with ozone, follow that up with something like zinc and acetic acid or something. The important step here is the O3. What does ozone do to double bonds? It's a very reactive oxidant, and it actually is so reactive it breaks apart the CC bond completely. What does it put on either end? A double bond. Not a carboxylic acid, but it's double bonded oxygen. So in this case, I start with a ring molecule. If it were not a ring, it would break apart into two molecules. Since it happens to be a ring, they're going to be connected together. So let me draw it. You're going to, where the double bond used to be, now we have a double bonded oxygen. Okay. Notice the group that's, I'll draw this out, the group that's on there are hydrogens in this case. So those hydrogens still remain. It's broken the CC double bond. Okay, that's an ozonolysis reaction. By the way, our water treatment plant, you know, they use very, very little chlorine. Our water is not chlorinated. They use ozone to treat the plant because that also destroys all those bacteria and microbes. And it tastes better because you don't have chlorine. Now, we talked about with alkynes in chapter 9, the reaction with, let me see, let me just take an example. The reaction with ozone. So if I take something like this, 1, 2, 3, 4, 5, 2 pentyne, okay? And I carry out the same sequence of reactions, that is ozone. That second step just is what happens is you form an oxygenated intermediate which breaks it down to the CO double bond. Ozone with a triple bond, now since we have another pi bond, we have 3 bonds between the carbons, we have to break it to make 3 bonds to oxygen on either side. What kind of functional group has 3 bonds to oxygen? You had it. A carboxylic acid. So in this case, it breaks apart completely, breaks it apart to form 2 carboxylic acids. What do we have? One with 3 carbons. So there's our 3 bonds to oxygen, and the other side would have just 2 carbons, right? So those would be the 2 products. Okay, so they're really good, actually, in breaking apart. That's good diagnostic tools, too. If you have an unknown molecule, but you don't know where your double bond is, you do an ozonolysis to make aldehydes, you can see what size fragments you've made, or a triple bond, you can see what size carboxylic acids you made. Then you know where that triple bond or double bond was within the molecule. So that's oxidation reaction. What else can we do with triple bonds? We can oxidize them. We can also reduce them. So let's just take my favorite phenylacetylene. Oh no, let me take this one. I'll put a methyl group out there. So that alkyne, we could add hydrogen, right? And we have 3 ways to actually reduce that. We can reduce it with hydrogen and palladium, and the product is what? Yes, alkane. So the triple bond gets reduced all the way to alkane. So we have 3 carbons there, we have 3 carbons group. By the way, I don't think I mentioned this before. That benzene ring I'm showing, you might wonder why that's not reduced also. We haven't got to that chapter yet. That's coming up. Those have some very special stability, and they don't react the same way as normal double bonds. Okay, so be aware of that. I guess I haven't specifically mentioned that. We'll talk about that a lot coming up. So, okay, we can reduce partially, right? Lindlar's catalyst, yes. And really, that's all I need you to recognize. If I write hydrogen gas and Lindlar's catalyst, that's that special poisoned version of palladium catalyst with some other additives in it. That lowers the reactivity, so it only does the first step. Okay? And then, very importantly, what's the stereochemistry? We have a double bond. With Lindlar's catalyst, it always adds, with any metal catalyzed hydrogenation, transition metal catalyzed hydrogenation, the hydrogens always add on the same side. Okay, so we get the cis. We have to change the mechanism to get the trans compound, right? We can do this reaction to get the trans compound, but we need different conditions. Remember what those are? Ammonia is the solvent, yes, good. But we need something to transfer electrons. Lithium. Or any sodium metal will work also. Okay, the mechanism is a little more complicated. It goes one electron at a time to make the anion and the free radical and protonation and then another electron. But the result is you end up with a double bond, which is trans. Good. Okay, so reduction chemistry. I talked about oxidation. We have reactions of electrophilic addition, right? Like we did with double bonds. Let me just take propyne. Okay. We can do things like addition of HBr. What do you know about that reaction? If I add excess HBr, 2 or more equivalents. Well, if you carefully control it, right, the first one will do addition of H and Br across the double bond at one of the pi bonds. If you have more than one equivalent there, that second equivalent will go further. Notice the regiochemistry is Markovnikov selectivity, just like it is with double bonds. Bromine does add to the more substituted carbon. And the hydrogen, the less substituted carbon. And then the second one also adds that way. Okay, so you know how to make these dibromides where the 2 bromides are in the same carbon. Okay, how do you go back? Strong base. KOH, or even better, NaNH2. Either of those would work. So you can do 2 eliminations. If you want to make a double bond, you do 1 elimination. You want to make a triple bond, you do 2 eliminations. So you have to have 2 leaving groups. Okay, you could do that also if the leaving groups are on adjacent carbons, because they could eliminate in both ways. Same way. Okay, what if we want to do, what if I add Cl2? One equivalent. Cl2 does what? Adds chlorine. It adds anti, right. So the product, stereochemistry, in this case, we form a double bond. So the other chlorine on this other end has to be where? Down, yes. The hydrogen is in that position. So it'll form the trans dichloride. You can add a second equivalent. If you have excess Cl2, then you'll add 4 chlorines. Or you could do them sequentially. I could do that, and then I could add Br2. Now we no longer have a double bond. So there's free rotation. So there's no cis and trans, but we have bromine and chlorine on each end. You can mix and match all of these. HBr, HCl, Br2, Cl2. You could control adding one at a time or adding excess, and you could add them sequentially. Okay? So you can add 2 halogens, you can add a hydrogen and a halogen in whatever order you want. You have a lot of control over that. The other electrophilic addition, which you need to know, is the reaction of, I'll go back to this, phenylacetylene. Okay. What happens if we do hydration? I put that in quotation marks because it's not just water we add. But what happens if you hydrate a triple bond? What's the product? Add water to a triple bond, you get a ketone. Notice it's Markovnikov selectivity. The oxygen ends up on the more substituted carbon if it's a difference on the either end of the triple bond. But it doesn't stay as the OH, right? Because that second double bond forms initially. So if you add hydrogen and water across one of the pi bonds, you get the enol. And that's not stable. It quickly isomerizes. The hydrogen transfers to the carbon and the double bond transfers to the oxygen to the ketone form.
So that enol is nothing more than a transition state.
No, the enol is an intermediate. It's not a transition state. It exists. It's an intermediate. But we can't just do the adding water and acid. It doesn't work that well. We catalyze this with something. Do you remember? I think did we talk about that today or yesterday?
So mercury sulfate?
Mercuric sulfate, that's right. So the conditions are water, mercuric sulfate, and that's catalytic. And the mercury comes off. You do have to have acid too, so it's usually sulfuric acid because there's sulfate on the mercury. Those conditions. Mercuric sulfate. So just remember, the mercury is only temporarily in an intermediate. It doesn't stay there, and inevitably on every test that I ever give, having this reaction, someone will draw a product with mercury all over the place. So don't do that. There's no mercury in the final product. It eventually comes off. It just helps the addition of Hg and water first, and then Hg is converted to proton. Okay, actually, if you think about it, there's not a whole lot. Other than that, there aren't a lot of reactions that are really new. Just new nucleophiles we've talked about on the same substitution chemistry. So you do need to recognize reactants and know what they are. Be careful about distinguishing between what are reactants and what are just solvents or bystanders. Like in the tosylation, there's purity in there, but its role is only to absorb HCl. It doesn't add to your molecule. HMPA, those are DMF, DMSO. Those are solvents for SN2 chemistry. They don't end up in your product. They're what everything is dissolved in. So be real careful about what's drawn there and what are there and what the role is. Okay. Identify what are nucleophiles and what are electrophiles, and it can help you out a lot. Anything else I didn't cover? Did I get everything? No questions? All right. We'll see you tomorrow. I think I had, if you have looked at that last slide from yesterday's class that I didn't fill in, have you worked on that at all? We'll work on it tomorrow in class, and then maybe go through some of the old tests.